A few days ago, I was watching some YouTube videos and I ran across a video by Matt Parker on his channel Stand Up Maths. I believe the video was called, "Will a Falling Pencil Hit the Table?" So this is on Stand Up Maths. And I'll put a link below. So this problem completely nerd sniped me. If you don't know what nerd sniping is, look it up on the internet. I think you'll understand. So here's the problem that was posed in that video. We have a table, and there's the edge of the table, and a pencil sitting upright, right on the edge of the table. So there's the tip of the pencil. And we give the pencil a kick right at the bottom. So there's a force over a short duration of time. So this is like giving it a kick, technically referred to as an impulse. And we want to know what happens. Well, you can predict some of what happens. The center of mass, of course, once the pencil is not supported by the table anymore, the center of mass will fall along a parabolic arc, but the pencil will also rotate. So the question is, does the pencil hit the table as it's falling away? Well, after spending most of the night working on this problem, I solved it, and I'll show you the complete solution in a moment, but let me go ahead and give you an answer in qualitative form. First of all, if the impulse, the kick, is relatively large, then what happens is the pencil just falls away without hitting the table at all. Let me show you this simulation again, and I've added a trace to the tip of the pencil so that you can see, you can more easily follow where the tip goes and see that it misses the table. So that's what happens if you have a relatively large impulse. Now if you have a small impulse, so the kick just nudges the bottom of the pencil off the table, then the pencil falls and hits the corner of the table along the shaft somewhere. Now if I let the simulation continue, the pencil just passes through the table. The computer code doesn't know there's actually a table there. So, but of course physically the pencil hits the corner of the table and then bounces away. So that's the case of a small impulse or a small kick. Now for an intermediate size kick, what can happen is the pencil will spin around and the tip of the pencil will hit the top of the table. Once again, if I let the simulation continue, the pencil just passes through the table. But you can see that the pencil tip would actually hit the tabletop in this case of intermediate size impulse. Okay, so let's go through the math. And by the way, in this calculation, I'm going to use an XY coordinate system with the y-axis vertical and the x-axis is horizontal, with the origin right at the base of the pencil before it's kicked. So what we need to do first is analyze what happens to the pencil during the short time interval in which it's being kicked. During the kick. So this is a short time interval where delta t is small. Okay, now we know that Newton's second law always holds. dp dt is equal to the force, the total force, the sum of forces acting on the body. Now, during this short time interval, we can replace the d's with deltas and write this as delta p is equal to f times delta t. Now, this is what's referred to as the impulse. And I'll use the symbol I for impulse. And actually, during the short kick, all the motion and forces are all in the x direction. So let me just drop the arrows and just let P denote the x component of momentum and F is the x component of the force. The momentum before the kick is 0, so this change in momentum is just equal to the final momentum. So let's write this as the final momentum, and that's the x component actually, is equal to the impulse. We'll denote the impulse by I. Now we also know that the momentum of the body is equal to the total mass times the velocity of the center of mass. So let's write P as m for total mass, and let's write the x component of the velocity of the center of mass as x center of mass dot. So the dot denotes time derivative. So this is equal to the impulse. So this equation, of course, we can integrate forward in time. After the kick, there's no more forces in the x direction, so the x component of velocity is just constant, equal to I divided by m. So this tells us that the center of mass as a function of time is equal to I over m times t. Likewise, we can find the y component of center of mass. The y component is just subject to the acceleration due to gravity. Subject to gravitational acceleration. Little g is 9.8 meters per second squared. So y sub cm as a function of time is equal to the initial value of y sub cm. Now let's see. Let's let the pencil have a length of 2a. So the center of mass is at a height a above the origin. So this will be a minus 1/2 gt squared. And now for the rotational motion, we can see here that we'll just use, the force is being applied at a distance a from the center of mass. So we find that using Newton's second law in angular form, dl dt equals tau. Okay, again, it's a one-dimensional problem, and we can replace the deltas with d's. So this is saying the change in angular momentum of the pencil during the short time interval of the kick is equal to tau times delta t, but tau is just f times a, the lever arm distance. So this is just f times delta t is the impulse times a. The angular momentum before the kick is 0, so just after the kick it's L, and let's call that, well, that's the L just after the kick, and it's constant once it's been kicked. There's no more torques acting on the body, so this just stays constant. We know that the angular momentum of a rigid body is the moment of inertia times the angular velocity, and I'll denote the angular velocity as theta dot. So let me draw another picture of the pencil here. Let's see, this is the pencil as it's flying through the air, and we'll let this be the angle theta. Okay, it's the angle that the tip of the pencil makes with the vertical direction. So that defines the orientation of the pencil. And theta dot is the angular velocity. And we also know for a uniform rod, like a pencil is fairly uniform, that the moment of inertia is 1/3 the total mass times the half length squared, a squared. Okay, so if we put this together, we have this equation becomes 1/3 m a squared times theta dot is equal to I times a, or in other words, theta dot is equal to 3I divided by ma. And because theta dot is it's a constant in time, once it's been kicked, we can just integrate this and find that theta as a function of t is 3I over ma times t. So now we have a complete characterization of the motion of the pencil. Let me rewrite the equations for the center of mass. The x component was I over m times t, and the y component was a minus 1/2 g times t squared. So next what I'd like to do is write down the equation that tells us where the tip of the pencil is as a function of time. Okay, the x component of the tip of the pencil, and let me call it just x without, I could put a subscript TIP, but I won't bother. This is just equal to the center of mass minus a times sine of theta. All right, and you can see that fairly easily. Let me just draw the pencil once again. So here's the center of mass. And this is the angle theta. So the location of the tip of the pencil is, its x-coordinate is the x-coordinate of the center of mass minus this distance right here, which is a, the hypotenuse, times sine of the angle theta. And similarly, the y component of the tip is equal to the y component of the center of mass plus a times cosine of theta. So you add this distance right here to get the y component of the tip. So if we simplify these, we find x of t, and again this is for the tip, this is equal to I over m times t minus a times sine of theta, and theta was 3i over mat. And then y for the tip is y center of mass, that's a minus 1/2 gt squared plus a times cosine of theta, which is 3i over mat. Now it turns out that a nice way to write these equations is, instead of in terms of time t, we can write them in terms of the angle theta. After all, the angle theta it's proportional to t. It's linearly related to t. So let's write, instead of writing x and y for the tip in terms of t, we'll write them in terms of theta. And we'll use the fact that t is equal to then ma divided by 3i times theta. So t was ma over 3i times theta. So that gives us x as a function of theta for the tip is equal to I over m times ma over 3i times theta minus a times sine of, well, this is just theta. And y for the tip is a minus 1/2 g times t squared. That would be ma over 3i quantity squared times theta squared plus a times cosine of theta. So simplifying this, we have, and actually in simplifying, let me divide through by a. So let's write these equations as x over a is equal to, let's see, here the m's cancel and the i's cancel. The a has been brought to the left-hand side, so we just have 1/3 theta minus, and the a has been brought to the left, so that's just minus sine of theta. And for y, we have y, and dividing by a, this is 1. Let me write this term next, plus cosine of theta minus, we'll have 1/2 g times, let's see, there'll be an m squared. There's an a squared, but I've divided through by a, so there's just a single factor of a. And in the denominator, we'll have the square of 3i. That will be 9i squared, all times theta squared. Now, what I want to do is I want to define this group of constants. let me call this 2 divided by k squared. And there's nothing magic about this choice. Of course, the first time I went through the calculation, I just called this whole thing k, but then I later realized that the results would be a little bit nicer and easier to interpret if I let this group of constants be denoted 2 over k squared. And one reason why is because you can see here that k is going to be proportional to I, the impulse or the kick. So that's a good reason for using k. K stands for kick. Okay, so with this definition, let's work out just what k is. This would be 2 over k squared is equal to 1/2 g m squared a over 9I squared. So if we invert this, and let's see, we'll divide by 2 and then invert it, we'll have 4 times 9I squared divided by g m squared a. So in other words, k is equal to, what would that be? 6 times I over m times square root of g times a. Okay, now let me rewrite the equations for the tip of the pencil. We have x over a is equal to 1/3 theta minus sine of theta, and y over a equals 1 plus cosine theta minus 2 over k squared times theta squared. Now, but before I go on, let me just point out this first equation is really interesting. You'll notice it doesn't depend on any details of the pencil. Well, actually there's an A here, so the x-coordinate of the tip of the pencil, if you just scale it by the size of the pencil, A, then it only depends on the angle, the orientation angle of the pencil. It doesn't depend on the acceleration due to gravity. It doesn't depend on the impulse or the mass of the pencil. So you can ask questions like, for example, looking at this equation, at what orientation is the tip of the pencil equal to 0? In other words, back at the origin or just above the origin. And it will have a universal answer independent of the size of the pencil, the size of the impulse. The answer is the solution to 1/3 theta minus sine of theta equals 0. And this equation has a solution of theta equals about 2.279 radians. And this was a solution obtained in Matt Parker's video on stand-up maths. But let's analyze this complete set of equations for the tip. The key here is to determine what happens to the pencil, whether or not it hits the table. We need to follow the tip. And there are 3 cases. Okay, case number 1, when the tip reaches y equals 0, if it's the case that the x-coordinate of the tip is greater than 0, then that tells us that the pencil misses the table. Okay, case number 2, when the tip reaches y equals 0, we have x less than 0, and the orientation angle is greater than pi over 2, then that tells us that the tip hits the top of the table. Tip hits tabletop. Let me draw a picture. Actually, let me draw a picture of this case number 1 first. In this case, here's the table. And the pencil, when the tip reaches y equals 0, so there's the tip of the pencil, the x component of the tip is greater than 0. So that means the pencil has missed the table. For this case number 2, here's the tabletop. And when the tip reaches y equals 0, we know that x is less than 0. And furthermore, the orientation angle is greater than pi over 2. So the pencil is oriented something like this. Then case number 3 is when the tip reaches y equals 0, we have x less than 0 and theta is less than pi over 2. Okay, in that case, we know that the shaft of the pencil must hit the corner of the table. So here's a picture of this case number 3. Here's the tip of the pencil. It has reached y equals 0 with a value of x that's less than 0. But the orientation of the pencil is still less than pi over 2. So you can see in this case, it must be that the pencil has already hit the corner of the table along its shaft. So the shaft of the pencil hits the table corner. So in all three of these cases, we're going to be focused on the instant when the tip reaches y equals 0, and here's y equals 0, y equals 0. I found it easier to think about this problem if I made a distinction between the generic values of theta and the particular value of theta when y is equal to 0. So let theta naught, that's a theta sub 0, equal value of theta such that y equals 0. So in other words, if we go back to our y equation for the tip, it's just, if we set y equal to 0 here, we have the equation 1 plus cosine of theta naught minus 2 over k squared times theta naught squared equals 0. So this is the equation satisfied by theta naught, value of theta when y is equal to 0 for the tip. Now this equation we can write in a little bit simpler form by using the trig identity that says 1 plus cosine theta, or cosine theta naught, is equal to 2 times the cosine of the half angle. So that would be theta naught over 2. So then this equation becomes cosine of theta naught over 2 equals theta naught squared over k squared. And we can also rearrange this as k is equal to theta naught divided by the cosine of theta naught over 2. Now in principle, we would like to solve this equation for theta naught, and it depends on k. Don't know how to do that, but what we can do instead is we can draw a graph. So this is theta naught, and this is k, and we'll draw this from theta naught equals 0 up to pi. And the curve looks something like this. So it asymptotes to infinity when theta goes to pi. So we can read off from this graph for a given value of k, we can come over here and find the value of sort of reading this graph backwards. So this equation and this graph tell us for a given value of k what the value of theta naught is. That's the value of the orientation of the pencil when the tip reaches y equals 0. And we need to know what the x-coordinate of the tip is when the tip reaches y equals 0. And that's governed by the equation which was x over a equals 1/3 theta naught minus sine of theta naught. So if we plot this graph, so we plot x over a as a function of theta naught, And again, here's pi. This curve looks like the following, where this is the value we found before, the value 2.279, the value of theta when x is equal to 0. So now we can read off from the graph the behavior of the pencil. If theta naught is greater than 2.279, then when the tip reaches 0, x is positive, which means that the pencil completely misses the table. And the value 2.279 here corresponds to a value of k of about 5.45. And we find that by just setting theta naught equal to 2.279 in this equation. We find k is 5.45. So the first conclusion is if k is greater than 5.45, then that tells us that theta naught is greater than 2.279, and therefore when the tip reaches the tabletop level, y equals 0, the x is greater than 0, and the pencil misses the table. Now for the second and third cases, we know that if theta naught is less than 2.279, then x is less than 0. So in other words, the tip of the pencil is to the left of the origin when the tip reaches y equals 0. Now whether it's the tip of the pencil that hits the tabletop or the shaft of the pencil hitting the corner depends on whether the orientation theta naught is greater or less than pi over 2. So pi over 2 is about 1.5. It's right in here somewhere. And we can find again from just plugging into this formula that when theta naught is pi over 2, k is equal to about 2.22. So if k is between 2.22 and 5.45, then we know that theta naught is less than 2.279 but greater than pi over 2, and in this case the tip hits the tabletop. And by the way, this value 2.22, it comes from evaluating this at theta naught equal pi over 2, so that's just equal to pi over the square root of 2. So this is pi over the square root of 2. And finally, if k is less than that value, 2.22, then we know that theta naught is less than pi over 2, which tells us that the shaft hits the table corner. Now finally, if we return to our definition of k, it's related to the impulse by the impulse is equal to square root of g times a times the mass m over 6 times k. So typical values for a pencil, we have the mass is about 6.5 grams. The length, that's 2 times a, is like 19 centimeters. And of course the acceleration due to gravity is about 9.8 meters per second squared. That's what, 980 centimeters per second squared. And we can see that these values of k, 5.45 and 2.22, we can see what they correspond to in terms of the impulse. And what we find is that for an impulse greater than about 806, that would be gram centimeters per second, then the pencil misses. For the impulse between about 328 grams centimeters per second and 806, the tip hits the tabletop. And then finally, for impulse less than 328 grams centimeters per second, the shaft hits the table corner. So there you have it, the complete solution to the question, will the falling pencil hit the table?